Welcome to week number 12 for ECE 111, Introduction to ECE. Today we're talking about things you cover in ECE 341, random processes. Basically, that's our course on statistics, on probability and hypothesis testing. Now, a random process is the following. Every time you do an experiment, you get a slightly different result, and that's true of most experiments that you're going to run. No matter how careful you are in setting up the experiment, you're always going to get slightly different results. For example, if I roll 10 six-sided dice, like cast a level 10 fireball, each time I roll the dice, I'm going to get a different answer. If I take a transistor out of a bin and measure the gain, each transistor's gain will be slightly different. These are random processes. Statistics is a branch of mathematics geared towards random processes. It allows you to analyze your lab data, which is part of the reason it's required to graduate. You'll be having quite a few labs in electrical and computer engineering. This is how you actually collect the data and analyze it. This lecture covers three types of tests. One is a chi-square test. That's testing whether something like a die is really fair. It's a test of a distribution. We'll also look at a t-test with one population. If I just have one set of data and I collect one more data point, what range can I expect that data to fall in? Or what's the probability that my next data point, like the next transistor that I take out of a bin, will have a gain greater than some threshold? And finally, a t-test with two populations, such as if I have two batteries, brand A and brand B, which one's better? There are tons and tons of other statistical tests, but really a t-test is the main one you'll ever use in industry, occasionally a chi-square test, but there are actually others. Actually, there are a lot of others. So let's start out with a chi-square test. A chi-square test is a test of a distribution. With it, you can answer questions like, is a die fair? Was data fudged? The procedure to run a chi-square test is first, you collect a bunch of data. Then you take the data and separate it into n bins, and how you do that is kind of up to you. For example, if I'm rolling six-sided dice, I might make the bins each number. So I have 6 bins, the number 1, number 2, number 3. I could also make it, say, the even numbers, odd numbers, numbers less than 4, numbers greater than 4, lots of ways of doing that. But regardless, you separate it into n bins, then you count. For the data that I collected, how many times does the data wind up in each bin? Well, once I assume a distribution, I know what the bins are, I can tell you what the probability is for the data to fall in each bin, that's p. The expected number of outcomes in each bin is n times p, and what I do is I compare what's the expected number of occurrences in each bin minus the actual number of occurrences squared, divided by expected, add them all up, that's your chi-squared score. Then to convert the chi-squared score to a probability, I use a chi-squared table, or a website called Stattrack. Now this is what a chi-squared table looks like. On the left-hand side is your degrees of freedom. That's the number of bins minus 1. That's common in statistics. A single bin makes no sense. For example, if I roll the dice 50 times and I got 50 numbers, what does that tell me? Absolutely nothing. I've got to have at least 2 bins, such as I could say, are the numbers even, odd, greater than 3, less than 3? I need at least 2 bins. So 1 is meaningless, so that's number of bins minus 1. That's degrees of freedom. The probability of rejecting the null hypothesis is on the top, and your chi-squared score is right here. So for example, suppose I have sample size of 6. I've got 6 bins meaning 5 degrees of freedom. If the data is very, very different than what I expect, I'll get a large score, like 16.75. If that's my chi-squared score, that means I can reject the null hypothesis with 99.5% certainty. If the number is smaller, like 0.41, then the data is very consistent. I only have a 0.5% chance of saying that this is not a fair die. Okay, so let's try that. Previously, we looked at how to roll dice in MATLAB. I can use the function rand that generates a number between 0 and 1. 6 times rand is a number between 0 and 6. Ceiling rounds up. So this gives me the number 1 through 6. That's a 6-sided die. Is that really a uniform distribution? Basically a test of MATLAB. You can kind of guess, yeah, MATLAB's been around for a while, it's pretty well debugged. But let's check. let's roll the dice 120 times. That's what this I loop does, a for loop. And then count. If I get a 3, I'll increase the result of 3 by 1. If I get a 5, increase the result of 5 by 1. And keep going 120 times. When I'm done, I've got how many times I rolled a 1, 2, 3, 4, 5, and 6. I'll then, with the 120 rolls, I should get 21s, 22s, 23s. Form the chi-squared score. That'll be the expected, well, the actual results minus expected squared divided by expected. Add them all up. That's my chi-squared score. So for example, let's try it. Here's a MATLAB script with the previous code. I'm going to roll the dice 120 times and count how many times I got each number. When I did that, I got 22 1s, 17 2s, 17 3s, and so on. Chi-squared score is 2.4. Try it again, 6.2. Try it again, 1.7. It's a random process. Each time I do it, I'll get a different answer. Suppose I got this answer. Come on, puppy dog. Wakey, wakey. There we go. Suppose I got this answer. And a chi-squared score of 2.4. What does that mean? Well, to figure that out, I go to a chi-squared table. I've got 6 bins, meaning 5 degrees of freedom. My chi-squared score is 2.4, which is right in this region. That's really very typical. If the number is really, really large, I can be pretty certain this is not a fair die. If it's really, really small, my data is really consistent and actually a little bit too consistent. With a chi-squared score, you can actually tell whether somebody's cheating. If the chi-squared score is too low, then either I got really, really lucky or I fudged the data. So kind of word of warning for you. You can spot data that's too good. Typically it's in the middle, and that's what I got here, 2.4. So there it tells me no conclusion. Another way is if I go to a website called Stattrack. This is kind of like the statistician's playground. Go to stattrack.com and pull up a chi-square distribution. You'll get a table like this. Tell that I've got 5 degrees of freedom. My chi-squared score is 2.4. Calculate, and it'll tell you 0.21. So this tells me there's a 21% chance that this is a loaded die based upon that data. Basically no conclusion. To accuse somebody of cheating, you probably need to be like, a 90, 95, 99% certain. 21% certain is just random. Now, let's try a non-random process. Suppose instead of using the rand function, I just go through the sequence. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It looks like a legit die. I'm getting the numbers 1 through 6. Does the chi-squared score pick up that this is actually not a random process? Well, let's try it. If I do this, roll the dice 120 times, I'm going to get exactly 21s, 22s, 23s, 24s, and so on. The chi-squared score, when I do that, is going to be 0. What that means is that there's 0 chance that this is a loaded die. When the number is that low, either I got really, really, really lucky, or I fudged the data. So that's kind of one way you can pick up fudging. If the chi-squared score matches up too well, I can tell this is not a random process. I fudged the data, or I'm not actually generating random numbers. I'm just going through a sequence 1, 2, 3, 4, 5, 6. Now let's look at a loaded die. Well, this is actually a problem they have in Vegas quite a bit. If you go on eBay, you can buy loaded dice. What a loaded die does is they take the numbers like the 6s and drill them out and fill them with lead, cover it up, paint it so it looks like a normal die. And that's kind of a problem in Vegas. I actually read a book back in junior high about cheating in Vegas. It's kind of fascinating. This is what craps looks like. So in a game of craps, but they have this large table. People are placing their bets on the different numbers that come up. Depending upon which number you bet on, if that number's up, you get different payouts. When the person takes the dice, like right there, where's the die? Somewhere there's a die. Here they are. Here come the dice. Oh, it's exciting. Dice are being passed to the person who's going to throw the dice. They grab the dice. Notice he's being very careful which numbers are on the dice, thinking that will actually help determine what number comes up. Throws the dice. They've got to hit the back wall and bounce off. Well, the reason for that is some years back, somebody came up with a way to take the dice, cup them in your hands, make the bottom number a 6, and then when you toss the dice, give a lot of spin, and the die would just slide along the table. The bottom die would slide, staying with the number 6 up, and the top one would tumble and be something random. Well, if one die is a 6, that really affects the odds. Instead of the number 12 being 36 to 1 odds against, it's now only 6 to 1 odds against, and you can start betting on the number 12 and make money. Well, in Vegas, you're not supposed to make money. You're supposed to go there, have fun, and lose, not win. So they changed the rules of craps. Now what you had to do is you had to hit the back wall instead of just letting the die slide. Well, somebody else came along and developed the trick. They could take the bottom die, cup it in their hands, pull up the 6, toss it, and it would hit the corner and just smack into it. Bottom die would stick, top die would roll off. Bottom die is a 6. Again, that affects the odds. I can start betting and winning. Okay, so they changed the rules of craps. Now when you toss the dice, it has to hit like 1 inch above the back wall, then bounce off. And even then, well, that affects that kind of cheating. There's other forms of cheating. I can take the dice and start drilling out the 6s and fill them with lead. So now the 6 is extra heavy. It'll tend to be on the bottom more often than not. So the number 1 comes up more often than it should. Well, to cure that, instead of having these opaque dice, if you notice in the video, the dice were clear. The clear dice make it harder to drill out the 6s and not be really obvious. But you can still drill them out, just can't make it quite as obvious, that much lead. But I can still weight it. The other thing they do, you can find a 3, like right here at the 3. The 3 goes between the 6 and the 1 on this. This line goes between two of the different numbers. On the loaded dice, they rotate the 3. It's got to be subtle enough that the person managing the table doesn't notice that this is a strange die, but the person who's betting can spot that, hey, my loaded dice are in play. Change my bets. That's kind of why in Vegas they rotate the dice out every 10-15 minutes, just in case there's a set of loaded dice on the table. If you ever cup the dice in your hand so the dealer can't see them, they get really upset. They think that maybe you're switching the dice. If you miss the table and the dice go on the floor, those dice are retired. You can't use them anymore. They'll bring out a new set of dice, because if they lose control of the dice, they don't know what happened to them. Maybe they got switched. Even with that, at the end of the day, there's still quite a few loaded dice in the bins where they retired the dice. I'm not really sure how they got in there, but it happens. How do you test for loaded die? Well, what I could do is roll the dice a couple times and see, does a certain number come up more often than not? Well, I can do that in MATLAB. For example, with this code, this simulates a loaded die. When I roll the dice, 10% of the time, I'm always going to roll a 6. The rest of the time, 90% of the time, it's a fair die. Can I spot that 10% loading? Well, to determine that with a chi-square test, what I do is I collect a whole bunch of data, compare the actual results versus expected results squared divided by expected results, add them all up, compute the chi-squared score, and then check. If the chi-squared score is really high, it's probably a loaded die. So in MATLAB, what I can do, I could try it. Let's roll the dice under 20 times, see how many times I get each number, then calculate the chi-squared score. So if I try it, here my chi-squared score is 5.2, and there's the result. There's a few too many 6s right here. Try it again, 9.2, 8.8, 2. Again, toss the dice a couple times. I get a chi-squared score. Suppose this is my result. 17, 21, 23, 18, 15, 26. Chi-squared score is 4.2. Now go into Stattrack. I've got 5 degrees of freedom. Can I illustrate that? Here's Stattrack, just an absolutely great website. Statisticians love this boy. I have a chi-squared test, and kind of notice there's a whole bunch of other tests. We're just going to cover chi-squared and t. So here, when I click on chi-squared distribution, I have 5 degrees of freedom. My chi-squared score was 4.2. Calculate. Calculate. There we got 47% chance this is a loaded die. And note that if I had access to the source code, the MATLAB code, I know it's a loaded die. I can look at the source code and see that 10% of the time I'm rolling a 6. If I don't have access to the source code, I really can't tell with only 120 data points. If I get more data, like roll the dice 600 times, now the chi-squared score is 19. From Stattrack, I could be 99.8% certain this is a loaded die. So I can detect loading if I have enough data. But after 600 die rolls, I'm probably broke. I'll know why I'm broke, but I'm probably broke at this point. So it's actually kind of hard spotting loading. If you get too greedy, like 100% loading, if I'm rolling 6, 6, 6, 6, yeah, that's pretty easy to spot. 10% loading is pretty hard to see. Which brings up the question, how loaded is too loaded? Well, I can calculate that. Suppose I want to find out how much I can load a die and get away with it. Assume detect means 90% certainty, or a chi-squared score of 9.24 from a chi-squared table. Assume I'm going to get x too many 6s right here. Assume I'm going to roll the dice 60 times, so I should get 10 1s, 10 2s, 10 3s. I'm going to get x too many 6s, and assume the other numbers are distributed evenly. A lot of assumptions. If I do that, I can take the chi-squared score. 0.12x squared has to be 9.24. Solve for x, I get x is 8.77. So I get an extra 8.77 6s out of 60 die rolls, or 14% loading. If I load the dice with only 14% loading, 14% of the time you get a 6, otherwise it's a spare die, I can probably get away with it with only 60 die rolls. You can actually calculate how much you can cheat and get away with it. If you've ever seen the movie The Imitation Game, that's about the British breaking the German code Enigma during World War II. And as soon as they cracked the German code, they were thinking, hey, we can stop all the German subs from sinking our convoys. And our hero was saying, no, we can't. Because if we respond to every German message, they'll quickly know that we cracked their code, change the code, and we're back where we started. So here's the problem. If I never respond, there's no point in cracking the code. If I always respond, the Germans figure it out. How often can I respond without the Germans figuring out that I cracked their code? That's a chi-squared test. That is, how many times can I load the die? How loaded can I make the die? How many times can I respond without the Germans realizing that we cracked the code? So when you watch The Imitation Game, you now know what they're talking about. I'm going to use statistics to determine when I do respond and when I don't respond. Another feature of the chi-squared test. I can spot when the data is too good. For example, suppose I'm hired to roll the dice 600 times, but I'm lazy. So instead what I'm going to do, I'm going to only roll the dice 60 times and add 90 to the result. The result looks like I rolled the dice 600 times. I have 600 die rolls. The numbers are different for each one. Can I detect that I really didn't roll the dice 600 times? I rolled them less. Well, I could try that in MATLAB. I'm only going to roll the dice 60 times, add 90 to the results. 90 times 6 is 540, total is 600. It looks like I rolled the dice 600 times. Now calculate the chi-squared score. Well, when I do that, here's what I get. Here's my actual result. What I should get, chi-squared score is 0.12. From Stattrack, That corresponds to a probability of 0.0003, or 3,000 to 1 odds against. It's possible that I could get data that good, but it's really unlikely. It's 3,000 to 1 odds against. If I keep getting really lucky like that, people can be pretty sure I'm fudging the data. I'm not actually doing what I'm supposed to. I'm not rolling the dice 600 times. I'm rolling them less, and I'm fudging it. This is what happens with Mendel. Mendel did a study on seeds, trying to show dominant gene, recessive gene. The dominant gene was green, and I think it was smooth. The recessive gene was yellow and wrinkled. So what he would do is take a hybrid, so you have both the dominant and recessive gene, cross them, and then take the dominant gene, like green. Take all the green peas, cross them, take the green ones, throw out the yellow ones. Repeat 8 times, and call that a purebred. Well, as a purebred, there are going to still be some recessive genes in there, which are going to mess up his data. That never showed up in Mendel's data. And it didn't just happen once, happened over and over and over again, which kind of proves that Mendel was fudging his data. Mendel's argument was that, well, if he actually used the real data, people would never believe him, and he was right, so he had to have the data match the theory. That's not how you're supposed to do research. But regardless, Mendel was right, and we're pretty sure he fudged the data. The data was too good. So that's kind of a warning for you. With the chi-square test, you can spot people who fudge data. So here's a handout. Suppose I roll a 6-sided dice 90 times. So I should get 15 1s, 2s, 3s, and so on. This is what I actually got. Find the chi-squared score and determine whether this is a fair die. So carrying on, if you pause the video and picked up, what you should do or should get is, let's bring up this calculator. The chi-squared score is the difference squared, that's 3. 3 squared is 9, divided by 15, gives you 0.6. The difference squared is 5. 5 squared is 25, divided by 15, 1.67. Add those together. Difference squared is 2. 2 squared is 4 over 15, 0.267. 2 squared is 15, 0.267. What was that? 4 over 15. 10 is 100 over 15. 6.67. And 2 over 15, 0.267. That's 4 over 15. Total chi-square score is 9.73. If I then throw that in Stattrack with 5 degrees of freedom, I can convert the chi-squared score to a probability. So that's kind of how you use the chi-squared test. And that should get you through the first set of problems on the homework. A second test, probably the most common test you're ever going to use in electrical and computer engineering, is the student t-test. The t-test is a test of the mean. With the t-test, I can determine the 90% confidence interval for where your data is going to lie, such as if I have a battery. How much energy will it be in the next battery that I buy? How high can I jump? What range is that going to be? What's my reaction time? I can find the 90% confidence interval for a population's mean. Such as I have a bunch of resistors, what's the actual mean for my data? I can find the probability that a random measurement will be more than a threshold. For example, what's the probability that a transistor has a gain of at least 500? The basic assumption behind a t-test is that all data comes from a normal distribution. That's your standard normal bell-shaped curve, something you're probably very familiar with. Example, weights, height, resistor values, so on, follow a normal distribution. It's a pretty good assumption due to the central limit theorem. The central limit theorem states that all distributions converge to a normal distribution. We've seen that a couple times in this course. And once you have a normal, normal plus normal is normal. And you can see that. Suppose I have a uniform distribution like a 6-sided die. That clearly is not a bell-shaped curve. if I add up 8 six-sided dice, this is the probability distribution. There's your bell-shaped curve. Very quickly, I wind up getting to a normal distribution. And once I have a normal, if I take this and add it to another one and get 16 six-sided dice, level 16 fireball, that'll also be normal distribution. A normal distribution looks like this. This is the PDF of a normal distribution. That's what it looks like, normalized so that the peak is 1. Again, your standard bell-shaped curve. This is how many standard deviations you go left and right. The mean is the center, the average. The standard deviation is a measure of the spread. This is a standard normal distribution where the mean is 0 and the standard deviation is 1. If I have a six-sided die, I could use the normal approximation to determine some things. For example, suppose I were to roll 10 six-sided dice, cast a level 10 fireball. What does the distribution look like? Well, one way to do that is roll 10 six-sided dice. Another way is to use the central limit theorem and use a normal approximation. For a single die, the mean is just the average of your data. That'll be 3.5. The variance is the average of the distance from the data to the mean. So it's going to be 1 minus 3.5 squared plus 2 minus 3.5 squared, so on, divided by 6. The variance is 1.7. If I have 10 six-sided dice, the mean will be 10 times the average, 35, and the variance will be 10 times the variance of a single die, 17.07. The variance is the square of the standard deviation. Take the square root. That's the standard deviation. The z-score then is how far, if I have a bell-shaped curve, how far is my data from the mean in terms of standard deviations. So suppose I want to know what's the probability of rolling 45 or more with 10d6. What I would do is say how far is 45 from the mean in terms of standard deviations. And what I get is 2.41. If I use the standard normal table, I can see what 2.41 means, or go to Stattrack. Come on, go faster. Get an add. Okay, go away add. Go to Stattrack and pull up a normal distribution. And a couple ways to do this. I am 2.4198 standard deviations away. So 2.4198 standard deviations away. Standard normal has a mean of 0, standard deviation of 1. There's my z-score. Hit calculate, and 0.9922. So 99.22% of the area is to the left. The area to the right is 0.0078, 0.78%. So that's the chance of rolling 45 or more with 10d6. So here's a problem. Determine the 90% confidence interval for rolling at a level 10 fireball. Well, again, here's my distribution. I want to go left and right so that this area is 90%. Meaning the right tail is 5%, left tail is 5%. Go over here, go to 95%, that's the area to the left, is 95%, or 5% tails. I get 1.645. I need to go 1.645 standard deviations away from the mean. So the confidence interval is the mean minus 1.645 standard deviations, and the mean plus 1.645 standard deviations. So 90% of the time, when I roll a level 10 fireball, I should do somewhere between 28.2 damage and 41.79 damage. That's a normal distribution. A student t distribution is very similar to a normal distribution, but it takes sample size into account. If I have an infinitely large sample, I wind up with a normal distribution, so sample size of infinity is a normal. The degrees of freedom, this guy right here, is sample size minus 1. Kind of figure if I have a single data point, I can't estimate two parameters, the mean and the standard deviation, with one data point. I need at least two data points. So that's kind of what the degrees of freedom tell you. It's how many data points did you collect minus 1. The top is the probability, just like we had with a normal distribution. And the numbers in the middle are your t-score. Very similar to the z-score. The z-score would actually be down here. That's a normal distribution if I have an infinite sample size. Or I know the population's mean and standard deviation, like a six-sided die. If I don't know it and I do an experimental result, then I use these numbers. What this kind of tells you is that if I only roll the dice 2 times, I can get information. I've got to be really, really cautious. I have to go left and right to the mean 6.31 standard deviations, but I can still do something with it. If I'm willing to splurge and collect 3 data points, meaning 2 degrees of freedom, the t-score really drops. Then I get diminishing returns. What that kind of tells you is that once you get past 5, there's not a huge drop. So you might think to know what's happening with a product, I need to have an infinite sample size. You don't. If I only have 2 data points, I can tell you something. I'd really like to have 3, maybe 5 or 6 would be okay. That's important because when you're in industry, if I want to know what my product is, what I'm selling, I need to sample it. But everything that I measure is now used. I can't sell it as new. So if I measured everything, I'd have no product and go bankrupt. If I measure nothing, I have no idea what's coming off the assembly line. With only a couple of measurements, with even just 2 data points, 2 measurements, stuff taken off the assembly line, I can tell you something. I would really like to have maybe 5 data points, 5 products coming off. Those 5 I can't sell as new. I could probably still sell them on eBay and get more money for them, kind of how eBay works. But I need to get some data. And just a few data points are really all I need. So for example, let's experimentally determine the probability of a level 10 fireball doing 45 damage or more. Well, what you do is you roll the dice. So let's just roll them 5 times. If I roll the dice 5 times, here's what I got. I got a 37, 32, 40, 41, 36. For my data, find the mean, find the standard deviation. That's the MATLAB's command mean and stdev. I've got these 2 numbers. So here's what the distribution looks like. The mean is 37.2, and the spread, one standard deviation, is 3.56. I now calculate the t-score. So I've got distribution, 37.56. I want to know what's the chance of doing 45 damage or more. I find out what is this distance in terms of standard deviations. This is very similar to the z-score that we did before. It's called the t-score since I'm using the estimated mean from the data and the estimated standard deviation, just slightly different. T-score is 2.18. I have sample size of 5, meaning 4 degrees of freedom. So I go to a t-table, look up 4 degrees of freedom, look up the number 2.18, which is right about here, and that says 0.95. So the area over here is 0.95. So the area to the right is 0.05. 5% chance of doing 45 damage or more. I can also do that in Stattrack. In Stattrack, go to a t-test. I input 4 degrees of freedom. My t-score is 2.18. Calculate, and it gives you the actual probability, about 0.05. Second example. Previously, we had this code for calculating how many times I get a full house, And with 100,000 hands, I got a full house 129 times, 125, 145, 146, and so on. What's the actual probability of getting a full house? Well, from Wikipedia, I can see that the odds are 694 to 1, or in 100,000 hands, I should get 144.06, and that's kind of in this ballpark. If I didn't have access to Wikipedia, I could collect data and see how many times I got a full house after 100,000 hands. Now do a t-test. Here's my data. Find the mean, find the standard deviation. I've got 1, 2, 3, 4, 5, 6, 7, 8. 8 data points means 7 degrees of freedom. So again, I'll find the mean. Here's my data. There's the mean. There's the standard deviation, STD. Great abbreviation. Let's see. If I did one more time, I want to find out what's the 90% confidence interval for what this number is going to be. Again, it's my normal distribution. I want this area to be 0.9. Then I need to go left and right, so many deviations. From the t-table, again, I've got 7 degrees of freedom. Use a t-table, or at Stattrack, I've got 7 degrees of freedom, 5% tails. That gives me a t-score of 1.89. So we need to go left and right, 1.89 standard deviations, or I expect this number right here to be between 122 and 157 90% of the time. I can actually do the odds of actually getting a full house. So this is actually, instead of a single individual, this is a population. When I do this, I'm going to have a lot of variability. That's kind of what this represents. I've got a lot of variability. Each time I roll it, I could get a small number, could get a large number. It'll vary a lot. There is an actual average or probability of getting a full house. That was this number, 144.06. Can I determine that number experimentally? That's a population. What's the population's average? To do a population, the variance drops by the sample size, or the standard deviation drops by the square root of the sample size. So if I take the same mean, take the standard deviation, divide by square root of the sample size, I get 3.22. Again, I've got 7 degrees of freedom, so 5% tails means 1.89. I need to go left and right, 1.89 standard deviations. That gives me this number. So I can be 90% certain that the actual probability of getting a full house is somewhere between 133 and 145 out of 100,000. From Wikipedia, it's actually 144.06, but that's in that range. So likewise with Monte Carlo, I can tell you the actual odds of getting a full house, at least give you a confidence interval. It's got to be somewhere in this range. That's useful in industry. If I want to know what's coming off the assembly line, what's the actual average, this is the population. For everything coming off the assembly line, this is the population's average. If I want to know individuals, each one that comes off the line, how much is it going to vary, I don't divide by the square root of the sample size. And I get this. And that's useful information to know in industry. I can also do things like weather data. If I have 5 years of weather data from Hector Airport, I've got the high for the month of April. I can calculate the probability it's going to break 85 this coming April. And from the data, I've got a mean, I've got a standard deviation. From the t-score, how far is 85 from the mean in terms of standard deviations is 2.02. I have sample size of 6, meaning 5 degrees of freedom. Find the number 2.02, and it says 95%. So again, here's your data. My data average is 76 degrees. I'm looking at 85 degrees. So the area to the left is 0.95. Area to the right is 0.05. 5% chance it'll break 85 degrees this coming April. Which I can do a table or just go to Stattrack. At a t-table, I've got 5 degrees of freedom, t-score is 2.02, calculate, I get 0.9508. And that's kind of what it looks like. Again, I can do a two-sided t-test. What's the probability, what's the 90% confidence interval for the high in April? And again, I've got sample size of 6, meaning 5 degrees of freedom. 5% tails is 2.02. I need to go left and right 2.02 standard deviations. So 90% chance that this April, the high is going to be somewhere between 67 and 84 degrees Fahrenheit. And again, here's what the data looks like. The mean is right here. There's the spread. 5% chance left tail, 5% chance right tail. So here's a problem for you. The gain of 5 transistors is as follows. There's the mean standard deviation. What's the probability that any given transistor has a gain of at least 600? Well, to do that, I need to form the t-score. The t-score is how far is 600 from the mean in terms of standard deviations. Come back, stay, there. So I would have 600, 826.8 divided by 138.9. T-score is minus 1.6328. The plus minus, don't worry too much about. If I do the minus, that'll be the left tail over here. If I do the plus, it'll be this area. Go to Stattrack. So I have 4 degrees of freedom. My t-score is 1.63. Calculate. Get 0.9118. Or if I use the negative, I'll get 1 minus that. All probabilities add to 1. This will be the other tail. So it's 91% chance it will not be higher than 85. Calculate. Come on, you can do it. 9% chance it will be more than 85. Or more than 600. What's the 98% confidence interval for the gain of any given transistor? Well, there I want 1% tails. So 1% tails. My computer's being really slow. If I have 1% tails, I need to go left and right. Drum roll, please. Oh, this is exciting. Come on, you can do it. Come on, puppy dog. 3.75. So if we go left and right, 3.75 standard deviations, that'll be my confidence interval. So if I go 3.75 times the standard deviation, 138.9, I need to go left and right 520. So 826 minus. So the gain will be somewhere between 305 and 1346 with 90% confidence. So that's a t-test with one population. If I have two populations, like A versus B, the trick is to change the problem. I don't know what to do with two populations, but I do know what to do with a single population. So create a new variable W, where W is the difference between the two. The mean of W will be the mean of A minus mean of B. The variance of W will be the sum of the two. And this is the part that kind of confuses people. I've got two populations, A and B. The mean can differ but the spread will always increase because it could get a small a big B, and so there's a bigger spread. Bigger spread means a bigger standard deviation. It isn't the standard deviation that adds, it's the variance. So you add the variances, then take the square root. So suppose I have two sets of data from A and B. What's the chance that the next measurement of A will be more than the next measurement of B? Well, to do that, I take the two data sets, find the mean of A, standard deviation of A, mean of B, standard deviation of B. And if you look, this is what the distributions look like. So there is a chance they'll have a large B and a small a, but usually a is bigger than b, but not always. Now form the variable w. The mean of w is the mean of a minus mean of b. It will also be normal distribution. That's central limit theorem. So the mean is 8.13. Right here is 0. The area to the right of 0 is the probability that a is greater than b. W is greater than 0. I want to form this t-score. How far is 8.3 from the mean in terms of standard deviations? So that'll be 8.3 minus 0, or just 8.3, divided by 4.55 gives you 1.78. The degrees of freedom is roughly the smaller of the two. A has 4 degrees of freedom, B has 5 degrees of freedom. The smaller of the two is 4. There's actually a much more complicated formula you can do to get it exact, but it doesn't really change the results. Go into Stattrack. 4 degrees of freedom, 1.78. 4 degrees of freedom, 1.78. Calculate. And wait. Calculate. Come on. 0.92. So 92% of the time, A is going to beat B based upon this data. So that's just some of the things you learn. There's actually tons and tons and tons of more statistical tests. The t-test is the one you're going to use most of the time, occasionally chi-squared. The chi-squared test tells you, or is the test of a distribution. It can tell you, is a die fair? Is your data fudged? A t-test is the test of the mean. That's the main test you're ever going to use. It's the probability that the data is larger than a threshold. That's a one-sided t-test. It can give you the 90% confidence interval. That's a two-sided t-test. And it gives you the probability that A will be larger than B. That's creating your new variable W. Again, that's just some of the tests you can use in statistics. That's some of the stuff that you cover in 341 random processes. And this is actually a really useful course because anytime you collect data in lab and you want to analyze it, that's what this course is all about. How do you analyze your data? With that, that should be enough to get you through the homework for this week. And that's next lecture number 12 for 341 random processes.